Hello, I am Lin Zhou. First, I will present our work on identifying and clustering counter relationships of team compositions in PvP games for efficient balance analysis, which discusses how to quantify the game balance in PvP games. The problem of this paper is focused on how to check there are no too strong or too weak compositions in PvP games. The compositions can be the game combinations, like used heroes or cars before a game start. Our solution for this kind of problem is counting the number of non-dominated compositions by its domination. See this image. If a blue composition and another orange composition have their own advantages on different cases, then there is no domination. If the blue one can do better than the orange one in all cases, then the orange one is, say, dominated. It's a simple relation based on win rate, but directly counting this domination is expensive with O n power of 3 times complexity over all n compositions. Thus, we try to improve its efficiency and define two new measures. First, the top D diversity, just counting playable compositions within a rating system, given a tolerant win value gap. Another is the top B balance, which counting non-dominated compositions, considering counter relationships. Let's have some examples of these measures. For the top B diversity, if we can assign a strength rating to each composition, then we can find the top one and counting how many compositions are not too weak to this top one. We will use neural networks and body theory model to get these ratings. However, a scalar rating system cannot handle cyclic dominance, like the case in rock, paper, scissors. Then we have the top B balance. We try to identify counter relationships with discrete categories and checking the domination on these categories. With these approximations, we can reduce the computational complexity of these new measures. Here's the information of this paper. It's a long submission on TMLR from September 2024. We are a research team in National Jiao Tong University. It's called NCTU before in Taiwan. Today's storyline starts from having a brief view of game balance to get a motivation of our method. Then we introduce how to get the ratings and the counter categories for our measures. Next, we check the performance of these tools to guarantee a good accuracy on strength relations. Within these tools, we can check our measures formally and have more case studies on our games. Finally, we will conclude our works and also point out some potential future works. Now let's start our story. There are many factors for game balance in general. For player, we have some goals to play a game, such as getting victory or success. Also, some players may argue the fairness or favor some diversity. From the role of game designers, they will want to improve the player experience, which is the basic of game design. Also, if they want to keep a good market competitiveness, they may want to update the game content. If we check these factors carefully, there are some trade-offs. Players who want to get victory, they will focus on some strong strategies and leading to these play styles. For game designers, they may want to simplify a game to provide a better learning curve for beginners. However, players usually want to have diverse and new contents to have more play styles. Then how to get a proper balance is such a kind of problem in game design and operations. We focus on the balance of compositions in PvP games, especially in a zero-sum game with two teams. A team composition is a game combination selected by players before a game start, such as the hero combinations in mobile games or the used card or so-called a deck in card games. We want to focus on the balance with least subjective factors, and using win rates is a choice. In common sense of game players, if a game has a bad balance, most players will only play the best compositions. If the game has a good balance, then players will have more playable choice with decent strengths. Then, how can we define strong or weak? We need some quantification index, like win rates or strength rating. However, directly using win value is not precise for strength. For example, winning a beginner and a champion are the same in a win count. But it's clear that winning a champion is very strong, but winning a beginner is nothing. So, using a rating system can handle this problem. Common rating systems like L rating, True Skill, or MMR are common in PvP matchmaking, and they are related to the broad data model we will introduce later. But solely using a rating system cannot handle games with secret dominance, or so-called intransitivity of win rates, like the case in rock, paper, scissors. To handle this problem, we propose a novel idea using a counter depot to capture some shared relationships. Broad model is a simple probability model. We can predict the player I wins the player J with their strengths gamma I and gamma J. These strengths are commonly reparameterized in ratings with exponential functions to guarantee a positive strength. This formulation is simple. Then, how can we learn this rating from win-loss outcome? We can use the common L rating updates rules or just apply simple regression to this model. It's important to use a neural network since we want to know the strengths of each composition. You can see that, for example, in League of Legends, there are so many team compositions. We need an approximation to generalize some unseen case. We use neural network with Simon structure to learn their ratings from match outcomes. Now, we can have a strength rating for each composition with this approximation. But don't forget that a secret dominance scenario is common in games, and using a rating system cannot handle this problem. If we directly maintain a pairwise win value, then the win value table may be too large. Then what can we do? Think about a Pokemon case. There are thousands of Pokemons, but players will not directly memorize which one Pokemon counter which one. We will think about their types. Here is the counter table of Pokemon types. Human players intuitively grasp counter relationships without the need for memorizing a super large table, but just like a simple table like this one. Then we think that, how about using a smaller n by n counter table instead of the 4n by n table? We use the residual win value after the broader material model to capture this counter relationship that a broader material model cannot handle. And a VQVAE is a kind of end-to-end classing method, and it can help us to create this discrete counter table. Here's the workflow of learning neural counter table. First, we learn the neural rating table from compositions and match outcomes. Then, we use discrete orientations to cluster those residual win values that a rating table cannot handle. We also make sure this residual value is symmetric and bounded in a reasonable region in our implementation, like use hyperparatension and the tree format. Now we have some tools to estimate win values in PvP games. Let's check their error curves. We design a simple combination game. There are 20 elements. You have to select 3 integers from 1 to 20 as a composition C. Each composition has a score according to the sum of those 3 integers. And we can sample a binary win-loss outcome from the rules. We also use the standard rock, paper, scissors as a toy game in our experiments. And combining these 2 games, we have an advanced combination game. It follows the rule of simple combination game, but only one modification. Each composition is assigned to a category corresponding to the rock, paper, or scissors. And the winner of rock, paper, scissors in a match will get 16 score bonus in getting a win-loss outcome. So there will be a game with clear counter relationship, but also have some complex compositions. Besides our toy games, we have popular online games like Age of Empires 2, the popular real-time strategy game. We consider the one-on-one random map across all player levels. We also use the records on HS Replay to test the balance of Hearthstone, the card game. Since the website provides the statistics of name deck, we only check the balance on these name decks, rather than all possible decks. It can be an interesting future work if those detailed card information is available. Also, we have mobile game, Brawl Stars, with complex compositions. It's a 3-on-3 game with different maps and different modes, and it's a clear example to have some generalization of rating to each compositions. Finally, League of Legends is still a popular mobile game with complex compositions. Since our task for game balance is to check the strength relation rather than give a precise win value estimation, then we directly evaluate the accuracy of strength relations. There are 3 cases for strength relations: weaker, stronger, and also the same level. We will compare our method to some baselines, including checking the win value with only one side. Just check a composition and its average win value. The higher one is clearly stronger. And also, another simple approach is that why not directly predicting the pairwise win values. And it also is the theoretical upper bound of accuracy with a high time complexity in game balance. Also, we have a linear version of neural rating table, which indicates the need of using neural networks to learning the strength of complex combinations. Here, we can see that using one side win value cannot get a comparable accuracy to the pairwise win value. On both training and testing dataset. In contrast, neural counter table NCT can have comparable or even better accuracy to the pairwise, since pairwise win rate may suffer from more fittings. In the games with clear counter relationships, like a game in Rock, Paper, Scissors, or Age of Empire 2, or some case in Hearthstone, there's a big gap between the neural rating table and the neural counter table. It indicates that our NCT can handle the problem of NRT for counter relationships. And also, we can see that in Brawl Stars, this game, a nonlinear approximation is required for complex game. Without the nonlinear part, just use linear body Taylor model cannot have a good accuracy. We further study on different sides of the counter table. A larger table can give better accuracy, sure, but a too large table will ultimately return to a high complexity. Thus, In real case, just choose a minimal size but also acceptable accuracy of the counter table size. For example, in the game rock, paper, scissors, we just only need a m equal to 3 and is enough. For more complex game, then you may have to have a larger m. Then with these tools for game balance, we can formally check our measures now. Recall that validating the domination relation on all compositions requiring high time complexity or n power of 3 is because we need to check a composition C1 dominates C2 over all compositions, including the C1 and C2 themselves. So we need 3 follows. If we can use Broad-Detail model to formulate the strengths, then due to its scalar property, it's simple to identify the max rating, and it will dominate all the others with lower ratings. And then we can find the top one. And this information for the top one is enough to many game balance techniques, like weaken the top one or increase others. Now check our top D diversity. We want to count the number of playable composition. But it's playable. A composition is not the best, but you still want to play it. For example, you may believe some compositions have high potential to win, and you can practice more or master it, or just have a good luck to win. Then that is a playable composition. You will have a tolerant gap in your mind to believe it is possible to win. Then we can count these compositions with the lemma 5.6. It's just use Broad-Detail model and add a win value gap for compensate this original win rate to larger than the half. Here's an example. The top one is A with a rating 1.8, and we give a tolerant gap 5%. Then the top D diversity is 4 in this case, since there are 4 compositions are not considered dominated by the top one. Actually, we do not need to sort the ratings, just find the max rating in ON time and check all composition, and it's also ON time. Then the time complexity of this measure is ON. If you want to consider counter relationship, let's check the top B balance. We first rewrite the domination relation with rating table and also a counter table in proposition 5.8. If 2 compositions are in the same category, then we just need to check the ratings in their case, and the top one in a category dominates its category. Also, if one composition is dominating another, like this case, the blue one dominates orange one. If there is another composition is inside the orange or so-called is dominated by the orange one, then it's clearly also dominated by the blue one, and it's the transitive property of domination in the proposition 5.10. Thus, we just check the top one in different categories in games balance, and it's the lemma 5.11, just checking the top one of each category, and we can get a domination. We have an example here, getting all ratings and categories of each composition first, and we can identify the top one of each category and perform domination checking. But now it's not all n power of 3, but smaller all n power of 3. And this thing only costs O(n) time, and identifying the max is O(n) plus m time. Thus, the time complexity of top B balance measure is O(n) plus m power of 3. Then let's have some case study. We try to check that the category is what? in a game, like in the Age of Empire 2. We find that it's reasonable. It's clustered by the advantages of civilizations in that game, and it meets the common knowledge of this game. If you are interested in this part, please check out appendix. And still in the Age of Empire 2, we can find that the Romans has the top 1 rating. Then, since it's top 1, do we need to make it weaker for a better balance? Not necessarily. If we can see that the top D diversity increased gradually, and it looks like smoother, and the gate of the G increased and the top D gradually increased. If we can keep the standard deviation of win value more than 4%, it seems that there are so many civilizations are playable. Then we check another measure, top B balance. Especially in the case with m equal to 9, the table size, there's a category dominated, and it's the category with good economic bonus. And even the top 1 posts in that category cannot have a competitive to other top 1s. Then thus we would suggest that the game designer to consider increasing all civilizations in that economic category with their economic bonus to maintain their counter relationships, but also increase the top B balance. Then it's clear that changing economic bonus is more important to change ROMs for better balance. And we also have counter relationships in Hearthstone. You can see that the counter relationship in Hearthstone is still complex. And the top 1 deck is the Treant Jury. Even with the large tolerant gap G, the top D is still small relative to all possible cases. Here we have so many decks, but with a G 8% is still not very high diversity. Then it's clear to change some decks in the Treant Jury, the top 1 deck, to have a better balance. And if we check the overall balance, the balance in counter category is good. There are some decks can counter the best Treant Jury, but overall it's still generally too strong. Overall, we have new balance measures now. We propose 2 new balance measures and the related techniques to compute them efficiently. And actually, we also propose a technique in discrete representation learning, but we skip here for the presentation. There are many interesting future work can follow our balance idea. For example, how to building strong compositions, and also the strength of individual elements like the 1 card or 1 hero is also very important to players and designers. In addition to game or competitive scenarios, we can have balance problems. For example, in board games like MLB or NBA, they have their rules to prevent a too strong team. Also, in a large language model evaluation, error rating is a common approach now, but maybe some models have their advantages on specific tasks, but overlooked by the rating in theory. Or even more, how we can find some effective questions in those evaluations. And we also believe that balance can help the learning in multi-agent games. In Alpha Star, they have exploiter agents to help the main agent counter the weakness in the StarCraft 2. And it's a clear counter relationship application. These are so many applications, and I can imagine that, and not even to games like the pricing in the supermarket or the design of menu in a restaurant. That's overall of my paper, and I prepared some Q&A. For the first question, can we combine the top D diversity and the top B balance? And yes, you can. You may want to set different gates G to different categories. It sounds like reasonable for practical case. And another question, how to improve game balance with the top D and top B, how to use this. And for top D, like the Hearthstone case, if you say there is a step-like increasing trend, then you have to change the top one. If it's like the Age of Empire 2, the increasing trend is smooth, then you just consider change the weak compositions. And for top B, if you find that a category is dominated, then so if you want to improve B, then try to identify the shared attribute of this dominated category and improve them overall. And overall, thanks you for listening. It's all about our paper. And if you can give a star to our GitHub, it will be helpful to us. Okay.